Moving on to energy. We live in one massive perpetual motion machine known as the universe. The fact that we still use polluting fossil fuel stores in the earth, or the incredibly unstable nuclear phenomenon which gives very little room for human fallibility, is truly frightening. There are four main large capacity, base load, as they would say, renewable energy means which are currently most ideal as per our current state of technological application. These are geothermal plants, wind farms, solar fields, and water-based power. Due to time, I'm not going to explain what these mediums are, as I assume most know. I'm just going to run through the abundance comparison. Geothermal. 2006 MIT report on geothermal found that 13,000 zettajoules of power are currently available on the Earth, with the possibility of 2,000 zettajoules being harvestable with improved technology. The total energy consumption of all the countries on the planet is only about half a zettajoule a year. And this means literally thousands of years of planetary power could be harnessed in this medium alone. Geothermal energy also uses much less land than other energy sources. Over 30 years, a period of time commonly used to compare the life cycle impacts from different power sources, it was found that a geothermal facility uses 404 meters squared of land per gigawatt hour, while a coal facility uses 3,632 meters squared per gigawatt hour. If we were to do a basic comparison of geothermal to coal, given this ratio of meters squared to gigawatt hour, we find that we could fit about 9 geothermal plants in the space of one coal plant. And that isn't accounting for the vast amount of land that is currently used for coal extraction. You know, those huge holes that we see in the earth. And by the way, the beauty of geothermal, and in fact all of the renewables I'm going to speak of, is that extraction or the harnessing location is almost always the exact same place as processing for the power distribution as well. All hydrocarbon sources, on the other hand, require both extraction and power production facilities, almost always in separate locations, sometimes refineries as well in separate locations. In 2013, it was announced that a 1,000 megawatt power station was to begin construction in Ethiopia. We're going to use this as a base, theoretical for extrapolation. If a 1,000 megawatt geothermal power station operated at full capacity, 24 hours a day, 365 days a year, it would produce 8.7 million megawatt hours a year. The world's current annual energy usage is about 153 billion megawatt hours a year, which would mean it would take, in abstraction, about 17,000 geothermal plants to match global use. There are over 2,300 coal power plants in operation worldwide today. Using the aforementioned plant size capacity comparison of about 9 geothermal plants fitting into one coal plant, the space of 1,940 coal plants would be needed, in theory, to contain the 17,000 geothermal plants, or 84% of the total in existence. Also, given that coal accounts for only 41% of today's current energy production, this theoretical extrapolation also shows how in 84% of the current space used by coal plants, geothermal could supply 100% of total global power supply. Wind farms. It has been calculated that today, with existing turbine technology, which is improving rapidly, that Earth could produce hundreds of trillions of watts of power, many more times than what the world consumes overall. However, breaking this down, using the 9,000-acre Alta Wind Center in California as a theoretical basis, which has an active capacity of 1,320 megawatts of power, a theoretical annual output of 11 million megawatt hours is possible. This means 13,000 9,000-acre wind farms would be needed to meet total global demand of 153 billion megawatt hours. This requires about 119 million acres of land, or 0.3%, 0.3% of the Earth's surface, to power the world in abstraction. However, as some may know, offshore wind is typically much more powerful than land-based. According to the assessment of offshore wind energy resources for the United States, a report, 4,150 gigawatts of potential wind turbine turbine capacity from offshore wind resources are available in the United States alone. Assuming this power capacity was consistent for a whole year, we end up with an energy conversion of 36 billion megawatt hours a year. Given the United States in 2010 used 25.7 billion megawatt hours, we find that offshore wind harvesting alone could exceed the national use by about 10.6 billion megawatt hours, or 41%. And axiomatically, extrapolating this national level of capacity to the rest of the world's coastlines, also taking into account the aforementioned land-based statistics, it is clear that we can power the world many, many times over with wind, and quite practically. Solar fields. If humanity could capture 0.1% of the solar energy striking the Earth, we would have access to 6 times as much energy we consume in all forms today. The ability to harness this power depends on technology and how high the percentage of radiation conversion is. The Ivanpah solar electric system in California, it's a 3,500 acre field with an annual stated generation of about 1 million megawatt hours. If we were to extrapolate using this as the theoretical basis, as we had before, it would take about 142,000 fields, or about 500 million acres of land, to theoretically meet current global energy use. That's about 1.5% of total land on Earth. Deserts cover about 1/3 of the world, or about 12 billion acres, and they tend to be fairly conducive to solar fields, while often less conducive to life support for people. Given the roughly 500 million acres theoretically needed to power the world as noted, only 4.1% of the world's deserts would be needed to contain these fields. Land that pretty much just otherwise sits there. Water-based power. There are 5 dominant types of water-based power: wave, tidal, ocean current, osmotic, ocean thermal, and water course. Overall, the technology for harnessing ocean in general is in its infancy, but the potential is vast. And based on traditional estimates, here is what the accepted global potentials have been estimated at, using existing methods. We're not applying advanced technology that's not in application yet. This all figures up to be about 150,000 terawatt hours a year, or 96% of current global use of the half of a zettajoule. Pretty much enough power to power the world in one medium alone, if applied. However, to give a sense of growing technological potential, because I think this is important, considering how, again, technology and water-oriented power is deeply in its infancy, recent developments in ocean current harnessing technology, the currents that go underneath the ocean, which can embrace much lower speeds now than they used to, it has been estimated that ocean current alone could now theoretically power the entire world if applied correctly. So let's recap. Wind, solar, water, and geothermal have shown, as large-scale baseload renewable energy mediums, that they are capable individually of meeting or vastly exceeding current annual global energy consumption at this time. And obviously a systems approach, harmonizing an optimized fraction of each of those renewables strategically, is the key to achieving a global total energy abundance. For example, it's not inconceivable to imagine a series of man-made floating islands off select coastlines which are designed to harness at once wind, solar, thermal difference, wave, tidal, and currents, all at the same time and in the same general area. Such energy islands would then pipe their harvest back to land for storage and distribution. It is only up to our design ingenuity to figure things like this out. Localization and reuse. The final energy factor I want to mention, which builds upon this systems thinking explicitly, has to do with localization and reuse schemes. Localized energy harnessing isn't given a fraction of the attention it needs today. Smaller scale renewable methods which are conducive to single structures or small areas find the same systems logic regarding combination. These local systems could also, if need be, connect back into the larger baseload systems, creating a total mixed medium integrated network, which happens sometimes today with solar. There are many localized systems out there which can draw energy from the immediate environment. Of course, there's solar power arrays, there's small wind harvesting systems, localized geothermal heating and cooling, and even architectural design that just simply makes natural light and heat-cool preservation more efficient. Buckminster Fuller was great with his dome structures and how they actually contain energy quite well. Same idea. Extending outwards to city infrastructure, we see the same wasted possible efficiency almost everywhere. A simple technology called piezoelectric is able to convert pressure and mechanical energy directly into electricity. It's an excellent example of an energy reuse method with great potential. Existing applications have included power generation by people simply walking on these engineered floors and sidewalks, streets which can generate power as automobiles cross over them, and train rail systems which can also capture energy from passing train cars through pressure. It has been suggested by people that have studied this that a stretch of road less than 1 mile long, 4 lanes wide, a highway, and trafficked by about 1,000 vehicles per hour can create about 0.4 of a megawatt of power, which is enough to power 600 homes. Now extrapolate that out to the bulk of all the highways in the world. You have a very, very powerful regenerative energy source. Overall, if we think about the enormous mechanical energy wasted by vehicle transport modes and high traffic walking centers alone, the potential of that possible regenerated energy is quite substantial. And it's this systems thinking, once again, that is needed in order to maintain sustainability while also pursuing this global energy abundance.